In this video, we will learn application of Gauss's law to find the electric field intensity due to a system of charges if the system has some symmetry. To find the electric field using Gauss's law, we have to follow some steps. Step 1. Draw a Gaussian surface. Step 2. Find the electric flux through the Gaussian surface. Step 3. Equate the electric flux to the charge enclosed divided by epsilon naught, that is, electric flux is equal to Q by epsilon naught. Then we need to know what is Gaussian surface. The surface that we choose for the application of Gauss's law is called Gaussian surface. Gauss's law is applied on this surface. It is a closed surface which passes through the point where electric field is to be determined. The magnitude of electric field intensity at every point on the Gaussian surface is same, and its direction is either along area vector or perpendicular to area vector. Now we will find the electric field due to electric field due to uniformly charged cell, that is hollow sphere, at every point near the hollow sphere or cell. The point may be outside or inside the cell. The two cases are there. First case, when or if distance of the point from center of cell, that is a small r, is greater than radius of the cell, that is capital R. It means the point lies outside the cell. Outside the cell. Consider a hollow sphere or cell of radius r, capital R. The Q charge is uniformly distributed over the surface of the cell. Suppose Q is positive, so total Q charge is uniformly distributed over the surface of hollow sphere. There is a point P which is r distance from center of hollow sphere or cell, and P lies outside the hollow sphere or cell. We have to find the electric field intensity at point P using Gauss's law. For this, we first need to draw a Gaussian surface. Here the Gaussian surface will be a concentric sphere. Here the Gaussian surface will be a concentric sphere of radius r. So we draw a concentric sphere of radius r, and this is the Gaussian surface. Gauss law is applied on this surface. By symmetry, you know that the direction of electric field lines are radially outward at every point on the Gaussian surface. Also, the magnitude of electric field is same at every point on the Gaussian surface, as each point of the Gaussian surface are equidistant. By symmetry, suppose the electric field at any point on the Gaussian surface will be E. Electric field, magnitude of electric field is suppose E, and its direction is outward, radially outward. Electric flux through the Gaussian surface, electric flux through the Gaussian surface integral E dot ds. This is a closed integral, as the Gaussian surface is a closed surface, and according to definition of dot product, it is equal to integral E ds cos theta. The value of theta can be determined by drawing a area vector. Suppose a very small area ds at point P. The direction of the area vector is outward normal direction, that is along the direction of electric field intensity, and this is ds vector. The angle between electric field and ds vector is 0 degree. Therefore, we can write integral E ds cos 0, and value of cos 0 is 1. Also, the electric field is constant, that is same at every point on the Gaussian surface. So E comes out of the integration, and it is equal to E integral ds. Integral ds is equal to the surface area of the Gaussian surface. The surface area of Gaussian surface, which is a sphere, is 4 pi r square. So total flux through the closed surface, closed Gaussian surface, is E into 4 pi r square. Now apply Gauss's law, that is according to Gauss law. Gauss's law, total flux phi must be equal to Q internal divided by epsilon naught. Value of electric flux is E into 4 pi r square. E into 4 pi r square is equal to Q internal, means total charge enclosed inside the Gaussian surface. You can see that total Q charge is inside the Gaussian surface, so Q by epsilon naught. and here we can solve that E is equal to Q by 4 pi epsilon naught R square, and its direction is radially outward. Thus we find the electric expression for electric field due to a uniformly charged cell at a point outside the cell. Now, second case, that is, if R is less than capital R, it means the point lies inside the cell or hollow sphere, inside the cell. Consider this is a hollow sphere of radius r. Q charge is uniformly distributed over its surface. A point P lies r distance from, this is capital R, small r distance from the center of a sphere. This point is P, and this point is inside the hollow sphere. We have to find the electric field intensity at this point using Gauss's law. For this, again we need to draw a Gaussian surface. Here Gaussian surface will be a concentric sphere of radius small r. We can see that charge inside the Gaussian surface is 0. There is no charge inside the Gaussian surface. Net charge inside the Gaussian surface is 0. Therefore, we can directly apply Gauss's law, that is integral E dot ds is equal to Q internal by epsilon naught. But we have Q internal is equal to 0. But Q internal is equal to 0. Therefore, integral E dot ds is equal to 0. And electric field is equal to 0. It means there is no net electric field inside a uniformly charged cell. Now we will find the electric field due to a long straight uniformly charged wire using Gauss's law. Consider an infinitely long straight wire. Suppose positive charge is uniformly distributed over the length of the wire. We have to find electric field due to this uniformly charged wire using Gauss's law. For this, we have to draw a Gaussian surface. Here, Gaussian surface will be a cylinder of length L and cross section area A, and whose axis lies on the uniformly charged wire. The cylinder has three surfaces. Electric field lines are radially outward at every point on its curved surface. But on the circular surface, that is surface 1, the electric field is perpendicular to area vector ds. Similarly, on circular surface 2, electric field is perpendicular to the area vector. But on the curved surface, electric field is along area vector. The total electric flux through the cylinder will be equal to the sum of electric flux through each surfaces of the cylinder. The electric flux through Gaussian surface closed integral E dot ds is equal to electric flux through surface 1 plus electric flux through surface 2 plus electric flux through surface curved surface. For surface 1 and 2, electric field is perpendicular to area vector, so theta is equal to 90 degree, and for curved surface electric field is along the direction of area vector, so theta is equal to 0 degree. So we have cos 90 is equal to 0 and cos 0 is equal to 1, so we get in E integral ds. Electric field is same at every point on the curved surface of the cylinder, and integral ds is equal to 2 pi r L. According to Gauss's law, electric flux is equal to q by epsilon naught, but q is equal to lambda L, where lambda is linear charge density, that is charge on a unit length of the wire. Since L length of the wire is inside the cylinder, so charge on L length of the wire will be lambda L. Applying Gauss's law, total flux E into 2 pi r L is equal to lambda L by epsilon naught, and therefore electric field is equal to lambda by 2 pi r epsilon naught. Now we will find the electric field due to a sheet of charge using Gauss's law. Consider a large sheet on which positive charge is uniformly distributed over its surface. You know that electric field lines will be perpendicular to its plane and away from the sheet. We have to find the electric field due to this sheet of charge using Gauss's law. For this, we have to draw a Gaussian surface. Here, Gaussian surface will be a cylinder of cross-section area A and whose axis is perpendicular to the plane of sheet, such that area of sheet enclosed in the cylinder is also equal to A. The cylinder has three surfaces. For surface 1, electric field and area vector are in same direction, that is angle between electric field and area vector is 0. For surface 2, electric field and area vector are in same direction, that is angle between electric field and area vector is 0. But for curved surface, electric field is perpendicular to area vector, that is angle between electric field and area vector for curved surface is 90 degree. The total electric flux through the cylinder will be equal to the sum of electric flux through each surfaces of the cylinder. Electric flux through Gaussian surface is equal to closed integral E dot ds is equal to electric flux due to surface 1 plus electric flux through surface 2 plus electric flux through curved surface. For surface 1 and 2, theta is equal to 0 degree, and for curved surface theta is equal to 90 degree. So we have also electric field is same at every point on the cross section of the cylinder. So we get two E integral ds. Integral ds is equal to the cross section area of the cylinder, and we get 2EA. According to Gauss's law, flux is equal to Q by epsilon naught, but Q is equal to sigma A, where sigma is surface charge density, that is charge on unit area of the sheet. Since the charge on unit area of the sheet is sigma, so charge on A area of the sheet will be sigma A. Putting the values, we get 2EA is equal to sigma A by epsilon naught, and E is equal to sigma by 2 epsilon naught. The direction of electric field is radially outward if sheet has positive charge,